So I'm kind of going to give a talk that's a little bit different, maybe more for entertainment, but hopefully some of the things may relate to with the topic of the conference. Here's a picture from the province of Alberta, from the top of Mount Temple, looking at Moraine Lake and the Valley of the Ten Peaks and so on. Okay, so I'm a simple-minded person who loves Occam's razor, and I believe that God also loves simplicity, so he created a universe that is a very elegant way of producing wonderful sentient experiences. And I have especially wonderful experiences being in this conference. However, a simple whole can contain complex parts. So for example, a simple set of all natural numbers or positive integers contains integers giving binary encodings of the content of the Bible, of the Library of Congress, of all books ever written, of the archive, of everything on the internet, of all the data on all the computers in the world, etc. So each one you can, in some sense, some encoding to some integer, so it's just, one element out of this simple set. So the complexity, of course, arises from the choice of each of these particular integers out from the simple whole. So, okay, I'm having to do this. Perhaps the universe is similar with a simple whole but complex parts. Of course, there's the question of what selects the division of the simple whole into the complex parts. So, now I'm going to take an Everettian view that the wave function never collapses. I'm maybe not a full Everettian in thinking that there's some preferred basis, but at least Everettian in the sense that I don't believe in collapse of the wave function. So in the Heisenberg picture, there's one single fixed quantum state of the universe, and it might be, by universe I'll include if it's a multiverse, if it even has many different parts with different effective coupling constants and so on. But maybe I differ a little bit from traditional Everettians and think, instead of thinking of, quote, many worlds, there are instead many different actual existing observations. And for me, fundamentally, observations are sentient experiences, or sometimes I call conscious perceptions, all that you're aware of at once. But I'm assuming that each one of these sentient experiences, each one of these observations, have different measures, different positive measures, this mu k, which will be some function of the particular observation. O sub k is an observation or a sentient experience. So in some sense, these measures tell how much the various observations occur. But the measures are not determined just by the content of the observations. I can't tell from my present conscious observation what the measure is. That's something that should be given by a theory. We could try to look for a theory predicting this, and we may have many alternative theories we have to choose from. Okay, for simplicity, I'm going to assume there's a countable discrete set of observations, perhaps an infinite number, but I won't do a continuum just for simplicity here, and that the total measure is normalized to unity for each possible complete theory. So T sub I is a complete theory that gives the normalized measures for all possible observations. So ultimately, I think a theory should give measures, normalized measures for observations. Then for a Bayesian analysis, because we'd like to choose what's a reasonable theory that can express our observations, I shall interpret the normalized measures of each of the observation OK that each theory gives as the probability of that observation given the theory. So probability of the observation given the theory, which for the observation is, statisticians call this the likelihood of the theory. The likelihood is not the probability of the theory, but the probability of the observation given the theory. So now this is something that may relate to complexity, I don't know, but it's the map from the quantum state to the measures for observations could be nonlinear. And I think if people talk about it depending on entanglement and so on, maybe it would be. But here I'm going to assume, and to my mind it seems simpler to assume it's a linear relationship. And I've called this sensible quantum mechanics. I've also called it another paper for more popular thing, mindless sensationalism, because it proposes that what's fundamental is not minds, but conscious perceptions, these individual observations that we have. And they might crudely be thought of sensations, though they include more of what one's consciously aware of, like memories. But anyway, because it involves sensations and not minds, I'll call it mindless sensationalism sometime, just to give a sensational title for it. Okay, so...
Is that a circular definition?
I'm sorry? Yeah, it's maybe circular. Okay, so I'm assuming that this measure for this observation It's a functional of the quantum state, the expectation value of this operator, or just put the brackets for the expectation value of the operator without explicitly writing the state. So it's an expectation value of this, or I could write this operator as, well, an operator that depends on what the observation is. So here, the sigma is the quantum state of the universe, positive linear functional of quantum operators, and this is what, just to give it a word, I'll call it an awareness operator. It's the operator that gives the measure for our awareness, corresponding to the observation or sentient experience, the conscious perception also K. So the quantum state, okay, I'm using it in a more general sense than Lenny did last night. I'm allowing it to be a pure state, a mixed state, given by density matrix, or a C-star algebra state. Anyway, something allows you to get that. I guess gathered from last night that Lenny was saying that, okay, states should be pure states, so maybe being Canadian, instead of calling this a state, it's a province. But anyway, so mixed province or C-star algebra province. And the awareness operators, along with the linear relationship above, and a complete description of also the content, what the actual substance, they should all be given by a complete theory. Now, of course, we're nowhere near having this theory, but this is sort of the framework. If we did have a complete theory, I think it should predict the measures of all observations. And in some sense, it would say all these observations occur with the different measures. There's nothing really probabilistic about the theory, but to test it, we could take the normalized measure of our observation as if it were a probability, and use that as the likelihood in a Bayesian analysis. Okay, in postulating that the universe is simple, I'm postulating that the quantum state sigma and the complete set of pairs of the observation, that's the actual sentient experience, what you're aware of, including the qualia and all the details of what you're aware of at each time, and then the corresponding quantum operator of sentient experiences and corresponding awareness operators is simple, though most of the individual experiences and presumably these corresponding operators may be very complex. Just as a set of positive integers is simple, even though most individual integers are very complex. Now, presumably the complete set of logically possible sentient experiences is infinite. I don't know, but I mean, sure, I don't see any logical limit to it. And even if I restrict it to a countable set of discrete sentient experiences that can be labeled by a positive integer. I'm doing this for simplicity. I don't really know how to do Bayesian analysis of the continuum. I mean, you have to be in it, and that raises another. So for simplicity of analysis, I'm just assuming there's a countably infinite number of observations. It might not really be simpler from God's point of view, so my assumption of a countable set of discrete sentient experience is just a working hypothesis. I mean, you know, it depends what you call Kolmogorov complexity. It depends what your computer is up to some, some finite amount. And I don't know what computer God runs when if he's trying to say which is the simplest thing to do that will fit his purposes. Okay, if there's a countably infinite set of distinct sentient experiences labeled by the positive integers, then the average complexity of the individual members of any set in of them would be expected to be of order at least log n, such one can't distinguish in elements without at least these bits of information. You have these bits of information to distinguish the thing. And I'm taking the complexity of a member of the set to be in the order of the number of bits of information needed to select them. And I shall ignore order 1 factors like log 2. I'll be just kind of sloppy to write this. Now, this subjective experience suggests to me that my sentient experiences have rather large, but maybe not extraordinarily large complexity. I can see you, but I don't think in one experience I have detailed awareness of all the details of it. I mean, I can sort of see a lot of people here, and I can see, certain things I can be aware of at once, a beard and a striped red shirt, or yellow shirt stripe, and so on, but I'm not aware of all the details at once. So the amount seems as if it might be finite, though of course I can't rule out the possibility, for example, a very fine graining, say, of the pleasure I'm having of this talk. I mean, maybe there's not just discrete levels, but maybe it's very fine. I don't know, but at least it's hard for me to be sure that it's. So I'm saying that at least if I want to put a lower bound on the information, he's saying it's maybe not utterly huge. So, okay, if most of the information and most of my sentient experience is visual, which I tend to think it is, and if I assume that this information is not much greater than the minimum information for a change in my visual field that I would remember, then if I look at these digits, I can't, it doesn't seem to me that I'm really aware of very many of them. I'm sort of aware of some of the patterns, but probably not a huge number. So I don't know how many bits, you know, maybe I'm aware of 100 bits or 1,000, but I don't think I'm aware of a bit, you know, of a million bits. So in support of my subjective intuition that my sentient experiences are not too large complexity, one might argue that a Bayesian analysis favors theories in which the mean observed complexity is finite and not unnecessarily large. And, okay, the argument for that, let's first just say how I'm proposing to test theories. This is, of course, very much in principle, because we don't have any complete theories, but if we had a theory T sub I, then for each possible observation, then it each gives the probability for that observation. Given a theory and an observation, it should give a probability for that, or which is really a normalized measure, but I'm going to interpret it as if it were probabilities. Now, we have to do a Bayesian analysis, we have to have prior probabilities for the theory. As far as I can tell, that's subjective, but presumably most of us make them higher for simpler theories. So we would tend to say simpler theories have higher prior probability. I think, yeah. So by Occam's razor would favor that. Then if we use an observation K to test the theory, then this is then the likelihood of the theory. And by Bayes' theorem, we can calculate the posterior probability of the theory. It's basically the likelihood on the prior, and then you have to normalize it by summing this product over all possible theories. So that's what that would be. To get that, I mean, of course, you know, this is way down the line before we could perhaps do that, because we don't even know how to do this. We don't even know how to do this for one single reasonable theory. And then, of course, to normalize, you have to be able to do it for all theories for which you assign the positive prior. So we would like to get this posterior probability as high as possible by choosing a simple theory, high prior probability, that gives a good statistical fit to one's observations, high likelihood. So we have two things we're trying to do a trade-off for. Now, there's a likelihood cost if you have too many probable observations. So suppose a theory predicts that there's n observations, which I'm taking the sentient experiences, that each are at least as probable as the one used to test the theory, e.g. your observation. Suppose you're using your observation right now to test the theory, and your observation, of course, includes memory of everything you've learned about physics, or whatever you can remember right now about what you learned about physics. Well, in order for the sum of probabilities to be unity, the probability of the observation used to test the theory can't be greater than this, because there's in other observations in a higher measure. So it can't be greater than that. So taking the likelihood of the theory to be the probability that the theory assigns to that observation, then implies that the likelihood of a theory can't be more than 1 over n if it predicts at least n observations as least as probable as the one being used to test the theory. So this is my main argument against theories that give a domination of the total probability of observations by a vast number of Boltzmann brain observations. So if these Boltzmann brain really could have very different kinds of observations, if you have a huge number of them and they're at least as probable as say ours, then that means for the total probability to add up to unity, then it's diluted by all these Boltzmann brains. So Boltzmann brains might dilute us, but here my main argument is they dilute the probabilities. And they make the likelihood of such theories much smaller than better theories that exclude Boltzmann brain domination. So basically I'm saying that Bayes holds Boltzmann brains at bay. And I'm sort of, Sean Carroll has a paper out recently that he suggested, well, you should react because it makes things cognitively unstable or something. But I don't think you need to go to that. I think a Bayesian analysis by itself is sufficient to rule out theories that have huge Boltzmann brain domination, because it's basically predicting, well, I'm assuming at least that it's predicting a whole lot of disordered observations, whereas we tend to have more ordered observations, and if you have this huge number of disordered observations, then they're going to dilute the probability and reduce the likelihood. So that's basically my argument against theories that have Boltzmann brains.
this simultaneously rules out our most plausible current theories of cosmology, right? So this is a very...
Why?
Most theories of cosmology, expand out into infinite future with, that would eventually produce these fluctuations.
No.
Yeah, but there may be.
By what measure?
Yeah, there's a measure problem.
If you don't think Boltzmann brains are conscious, you don't assign them a big measure, then yeah, you can.
No.
But I mean, there's ways. I think Raphael has ways of regularizing, and I have maybe rather ad hoc and not very beautiful ways, but I have ways that you can regularize it to avoid having this domination. And I'm saying, okay, we don't know one that has a really high prior, but it changes the likelihood so enormous that even if we have sort of even a not very elegant way of getting rid of Boltzmann brains, even though that may make the theory more complicated and reduce the prior, because it has such an enormous effect on the likelihood, I think it's better than a somewhat simpler theory that has all these Boltzmann
You're
brains.
saying you want to get rid of them just by changing the measure and not by changing the cosmology.
Well, maybe. I mean, perhaps not by because there's this connection between the quantum state and the observations. These awareness operators. I don't know what they are, but it could be that there's properties in those that basically maybe gives low measure to things that are a long ways away from the Big Bang or a long ways away from the bounce if the universe started with a bounce. Anyway, I mean, okay, maybe it's a bit ad hoc, but if you somehow say that these operators, if in some sense if they're very far away from the Big Bang, maybe that they go down. It doesn't have to go down. I mean, you can have volume averaging where you don't count up all the observers, but you count each observers on a hypersurface and then divide by the volume of the hypersurface, so you get the density of observers. Or you can do thickened geodesics, which is a sort of equivalent. Yes?
Can I just comment? I mean, you don't even know whether they dominate or not before you specify both your theory and the method that you use to regulate the divergences. The method is really part of the theory, and then the absence or dominance of Boltzmann brains is a constraint on the combination of the theory and the measure, and there are very possible combinations that do not have this problem. Now, whether there's more of one or the other is hard to quantify. But
Well, I guess the whole measure thing seems so ad hoc in the first place.
Well, we don't. I guess I would say that we don't have nice, elegant theories for it yet. But in my case, this theory is including not only cosmology but also the measure. It's the theory of everything.
Yeah.
I mean, it's not the so-called TOE, which is a very weak form. That was just theory of dynamics. So-called particle physics TOE is very, very far away from a theory of everything. And it doesn't include the quantum state, and it doesn't include the rules for getting the measures of conscious experiences out. Okay, so suppose we have these prior probabilities for theories, and here I mean the full theory, including not only the dynamics, but the quantum state and the connection to consciousness. And then, okay, these conditional probabilities, these are the likelihoods, and then the posterior ones are that normalized. The prior ones are subjective, usually higher for simpler theories, but even if everybody agreed which is the order, you still have how to do the weighting. So the highest prior probability might, for a theory, I might think the highest prior probability would be for a theory that nothing concrete or contingent exists, just a blank. So, but that would give no observations. I mean, because observations I consider is logically contingent, or don't have to exist. So that would have zero likelihood. So that's why I throw that out. Now, another theory that some people say is that everything exists. And if I refine it a bit more, if I say that all observations exist equally, but there's an infinite number of observations, again, because if each one exists equally, but there's an infinite number, the probability for each one is 1 over infinity. So again, you get zero likelihood for that theory. Now the other extreme, which I don't think is correct either, is a maximum likelihood theory, and that would give if we use say you use your present observation to test the theory, if that were the only observation that really existed, if some theory predicted that, it would predict it as unit probability, because it would say that there's a probability 0 for all other ones. But it seems to me that this seems to require a very complex theory. If you imagine that only your present experience existed and no other ones, despite the fact that your experience includes seeing around that there's other people that look like they're pretty much, I look around and see all the rest of you, and it would seem to me require a very complex theory for imagining that you're all zombies and not conscious. So I think that would complicate the theory so much. It seems to be a much simpler theory to assume that all of you are conscious, at least if you're awake, and well, and also if you're dreaming. If you're asleep and dreaming, I think you're conscious too. But anyway, so I think this would have a very low, and so my mind is that and this would be a case where the prior would be so low that I'd rule it out. So there's a trade-off between the prior probabilities and the likelihoods, that is between intrinsic plausibility, that's the prior, and fit to observations, that's the likelihood. So, now, my Bayesian argument against Boltzmann-Brain domination, that they would dilute the probabilities of our observations too much, might also to be taken as an argument against multiverse theories. By producing vast numbers of additional sub-universes, they presumably give rise to many more observations with comparable probability stars. If the landscape is populated and there's other parts out there that have conscious beings, then you have to normalize the total measure, you have to include theirs. So they give many more observations with comparable, and that would dilute the probability of any of our observations and make the resulting likelihood of any multiverse theory much less than a single universe theory that also predicts the existence of this.
Does this also apply to planets?
Yeah, it would apply. It would apply. I mean, if the universe were, yeah, I mean, it would say the likelihood would be bigger if we had a small universe and there weren't any other conscious beings anywhere else that only occurs on Earth. So I agree so yeah. So I am saying that because I want the sum of the normalized measures to add up to 1. The likelihood is less if there is more out there. Yes.
Suppose you guys, it's very philosophical. Suppose you got lucky and measured strings at the LHC or something, and you got convinced that string theory was correct, and it also makes the prediction of a multiverse. How would you view that in your?
Well, just wait and see. I'm not using this to reject multiverses yet, but I'm just saying as far as the likelihood goes, it does make the likelihood a lot less.
It's a question about your philosophy.
Well, okay, yeah.
In other words, in most even the totally empirically established theories, you don't measure most of what the theory predicts. So with the multiverse, it could happen. I mean, I'm not optimistic that this would happen, but you could locally measure a lot about a theory, which also has the implication of a multiverse, which you never really directly see. How would you view that?
Well, I agree that seeing that observation would increase the likelihood. And so, despite what I'm saying here, you're going to find I'm not opposed to multiverses. But I'm saying that So certainly finding evidence that it fits string theory, and if you find that string theory predicts a multiverse, that's of course increases the likelihood.
Even though they're all.
I think Thorne is comparing theories that predict multiverses to theories that don't predict multiverses.
Right.
It has to be such a theory, and if there's a theory without the multiverse.
Or another way to put it, you're assuming that both theories contain a universe that looks just like ours. And the question is whether there's other universes. We could argue there's a compensating factor in the numerator, where if there's a multiverse, there's more different kinds of universes, and therefore our universe is more likely to appear. The way you're doing it, which is of course deeply controversial, but I'll just take that for granted. I think those two factors cancel the numerator and the denominator.
Yeah, so I'm definitely taking the view that you should get likelihoods in the theory. You don't say that the theory, because suppose the theory predicts that at least somewhere in the multiverse I exist. I'm not taking the view that that makes the probability unity, because I want these probabilities to be probabilities out of all possible observations. So it's sort of like as if someone randomly chose an observation out of the full set. What's the probability he would get mine? And that seems to be, the trouble is if you do it the other way and you say that, well, okay, suppose we have a theory that produces a universe or a multiverse so big that almost certainly you exist in that. If you then say the probability is that unity and you use that in your Bayesian analysis, you're going to essentially have unit likelihood for any theory that has this character. You're not going to be able to test it. It then reduces purely down to the prior probabilities, and science no longer becomes observational.
This is a different point. The point is doing it your way, doing it the way you want to do it.
Right.
It's still true that a multiverse is more likely to predict our observations, because our universe is more likely to appear in a multiverse than in that.
Then, sorry.
Then if there's, suppose you have a multiverse of 100 different universes with different
Okay.
laws of physics, okay?
Okay.
And I'll compare to a single universe,
Right.
okay? And suppose each of the 100 universes has one being with conscious experiences or something.
Okay.
So if you're comparing, the way you're doing it, if you're comparing it to a single universe that looks like us, then you would say the single universe is 100 times better. But if you don't know that the single universe would contain us, if it could look like any of the 100 universes, then now it's equally good.
Yeah, but of course, I'm also assuming this theory is an absolute complete theory. It means absolutely nothing to chance. So this complete theory specifies exactly what occurs all over the whole thing. So therefore, it's not leaving it to chance as to whether, so the theory, I agree to get any, the theory has to predict that we exist somewhere in it for it to have any likelihood that's
Right,
positive.
that just converts the same factor to a lower prior probability that you could find. That just reduces it back to Juan's point, that it might be much harder to find a single universe theory that explains our observations than a...
Right. That's what I think. That's going to be that's going to be my resolution to the thing. But I do think that we should take this into account. I don't think it's fair to just throw out a multiverse theory and says, well, we have a multiverse theory, it's so vast that it produces us somewhere in it. That's sufficient. I think you have to get you have to do the Bayesian analysis, and you have to get the product of the likelihoods and the priors up. And I am saying that there is a cost for the likelihoods, and I think it's a cost that should be paid. And right now, I'm tentatively willing to pay it. Yes.
Can I rephrase your statement here as saying that multiverse theories are more testable than ordinary ones, in the sense that there are more things that I can vary and that I can then find we may be very atypical in the probability distribution obtained from the theory? I mean, for everything that can actually vary and is not a fundamental constant,
Right.
I can ask the question, what is the probability distribution for the observations of that variable?
Right.
Conditioned on observers is still a non-trivial distribution where we might be in the tail. Right? So for example, I mean, there are tons of theories like this, like Abbott and ground title, why not ruled out because we don't see in every universe, and we should see that with overwhelming probability. I mean, I think you're just saying that there are more opportunities for something to go wrong if you have multiverse theory.
Yeah, that could be. Okay, I'm sympathetic to the people that say that some people object that when you produce a multiverse theory, if it explains everything, in some sense they say it explains everything and explains nothing. And if you take a naive view about that, I'm saying that that's not really the situation. It really should predict, for a viable one, it really should predict the distribution such that when you do take this distribution, you take the likelihood of ours and multiply by the prior, you get something that's high. And so if it's a theory that produces lots of Molson brains, that's not a good theory because the likelihood is very low. Okay, I'm not going to rely on the counter-argument that most of the alternate universes are not effective constants of physics fine-tuned, so that presumably they're not as efficient. Even though I believe that most of them do, I suspect there still leave a huge number of other biophilic ones. So, for example, if you take a common estimate, I understand that the estimates have gone up. I don't know what's the latest thing for is 10 to the 500. Is there some canonical number that the 10 to the 500 is now gone up to, or somebody?
It's really infinite. There are infinite number of topologies. It's not really.
Yeah. So this must be some restriction to even things that might be conceivably
If
viable.
people happen to have studied at a certain point, it's not.
Yeah.
Not meaningful.
Okay, so even if you said that there was something like that, and then that could have potentially something. So I'm trying to be generous to the people that say it's finite, that maybe there's a finite number that have some property, who knows? There might be, okay, so there must be some restriction there, because there appear to be mathematically consistent configurations with infinitely many topologies, I think that's he was saying. So if you need the cosmological constant to be roughly as small as it is, then perhaps something, since it's a roughly 10 to the minus 122, if it were evenly distributed, only maybe that fraction would happen. There might be other restrictions from effective coupling constants. Let's suppose, I'm just putting in numbers. I mean, as you say, you're not supposed to take any of these numbers literally, but suppose the fraction were as low as that. If there really were something like that or more, there's a huge number that would have, that could be biophilic, that could have life in it. So this is sort of a side you can, interesting, from these anthropic arguments, you can get crude estimates for things. The Carter and Carr-Rees found relations with stars. I don't have time to go into them. That the mass in Planck units, the mass of the protons roughly the electron chart or the elementary charts at 18th, and that's this. And then I found from using some papers of R.G. Flow that you could get a relation like that by assuming the unification mass is logarithmically near the Planck mass. If you put these three equations together, you get equations that if you take the approximate equations as exact, you're going to get an estimate for the charge of the electron or the absolute value that's within 2% of the actual value. And then you can also calculate other things. The mass of the proton, because it's raised to a large power, it's off by a factor of roughly 2, but the logarithms are only off by about 1% or so. And you can get the density of water and the masses of stars, all from this number, just mostly simple powers. I'm not going to give all the arguments and for the size of the universe and that, and the density of the dark matter and the number of stars. Well, this is one estimate from Wikipedia of how many there are, so it's off by a factor of 13. Gravitational wave strength from things across the universe, which is interesting, more or less the reciprocal of that. And the height of a giraffe, okay, that's more involved, but anyway, you can. That's the largest running animal that doesn't overheat. So anyway, okay. All right. So, okay, let's go back to this. If there's that 300 fire, then that means there's so many, that might reduce the probability of our observation by a factor of something like that. So that would reduce the likelihood of a multiverse theory, this particular factor, by a factor of a Google. But I'm personally hopeful that a good multiverse theory, with no need to specify unique definite values for effective constants of physics to produce this landscape, will be sufficiently simpler that it would be plausible to assign the prior probabilities much more than 10 to the 300 times greher.
That's a pretty big number.
Yeah, I agree. It's a pretty big. I guess I'm a pretty big number. I'm saying that if you really wanted to specify, you know, a huge number. Of course, we don't know what the constants, the fine structure constant and the mass ratios. We don't know what they are to a huge number of digits. But if you knew what they were and you had roughly 300 digits for these things or more, then saying that it's this particular value would reduce the probability. Well, I mean, it's subjective, but I think it's quite plausible that it would reduce the probability by basically 10 to the minus the number of digits that you say are expressed in that. So, anyway, I think that this factor 10 to the 300 can be accounted for by basically the priors, and of course it includes a fit to, you know, if you find that there's fit to string theory and so on. I don't think it works for Boltzmann brains, because if Boltzmann brains exist, I mean, one estimate for the action of something like a human brain size, if you produce the human brain in an antimatter, then this is roughly the density in Planck units. And throughout the future universe, if you say that it's not cut off by something, I mean, I agree that there are ways to cut it off, up to a time of that, or maybe even the exponential of the square root of that, that's a double exponential. It would reduce the likelihood of theories with Boltzmann brains far, far more than the single exponential number of sub-universes in the superstring landscape, well, assuming this really is finite. So I'm saying as far as the priors, you shouldn't worry about a Google cubed, but you should worry about a Googleplex. So I think we want to worry about giving up Boltzmann brains. Let's see how much, I started late, but how much time do I have?
6 or 7 minutes.
Okay, so let's see. So now another question is, if our observations are given by expectation values of operators, how non-local are there? Now, presumably it doesn't matter where a brain is. The operator whose expectation value gives the measure presumably involves some integral over space-time. And also ideally over the Lorentz group, although this brings into parts the fact that it's non-compact, so there's normalization issues. I don't know how to deal with that, but what I mean is how local a seed operator has to be. So suppose I said it's like a projection operator to some state of my brain, but then I take that seed operator and I integrate it over all possible locations for the thing. And possibly over the Lorentz group to get an awareness operator. But the question is, how big, is it sufficient for the seed operator to be just the size of a brain, or maybe there's just a relevant part of the brain that really is responsible for consciousness? Now sometimes people say a sentient experience takes a time of 1/10 of a second, and if you wanted to have a tube this way, if you wanted to express it on one spatial hypersurface, you'd have to have this tube that lasted 1/10 of a second, within some causal patch, and that would be, you know, a tenth of a light second across, or 30,000 kilometers. That would be a much bigger region. But it's not obvious to me why it couldn't be produced instantaneously. So I'm taking the view that if the configuration is right, it doesn't need to stay right for a tenth of a second. It just needs to be right for a very short time, maybe a Planck time if you doubt that instants really exist. So then I don't see any reason why it should take any significant time for the result of what's in there to give rise to the sentient experience, and so on. Now, an argument for non-locality is by having globally non-local seed operators, you can define them to give zero expectation value to the vacuum to avoid Boltzmann brane problem and empty space-time. Because it seems like if you have localized operators, any positive localized operator tends to have a positive expectation value even in the Lorentz vacuum. And I think that was one thing I pointed out about Boltzmann branes, not only in thermal de Sitter, but also just in the vacuum. So it seems difficult to do with localized, but if you had a global operator like the square of the total charge, then that would be zero in the vacuum. And so if our experience is really dependent upon something that's global like that, then you could perhaps avoid Boltzmann branes with that thing, but I find that very hard to fathom. It's very hard for me to imagine myself as infinite. So, I mean, it sounds too megalomaniac. So I tend to think that I localize at least the seed operator before you integrate over the space-time. So there's ways to weight it, I mean, that Raphael talked about, and I have some other ways. Now another question is entanglement, and here I'm have some skepticism about how the importance of entanglement. How much entanglement do we need? Well, if these seed operators are fairly localized, then they would be insensitive to quantum correlations over larger regions. They could, of course, certainly be sensitive to the state in the small region, and that state could include, or that province could include entanglement. But over larger regions, it doesn't seem like that they're important unless the operations are much more non-local. And of course, there's a logical probability that the probabilities are not given by expectation values of operators, but nonlinear functionals. And I was mentioning last night, even if it was an expectation value raised to a power slightly different from unity, that would be consistent with observations, though it wouldn't be so simple. So I'm not saying I believe it, but it's possible. It's that. So how much complexity do we need for observation? Well, it seems to be relative to some particular initial state. It's not clear to me what picks out this state. Or anyway, this is just some issues I don't yet understand about complexity. But my version, it doesn't give a preferred basis of quantum states, though these awareness operators do give a preferred set of operators. Perhaps there's some way to define the complexity of this set of operators relative to each other, relative to the quantum state, but this is beyond my understanding. So as you see, I don't have enough to really get into a lot of these very fun, interesting ideas that I've heard about complexity, but so it does raise questions. Okay, so let me conclude. The entire universe may be simple, but with complex parts. Observations may be individually complex, but form a simple set. The probabilities might be given by the expectation value of positive awareness operators, also individually complex, but forming a simple whole. These might be integrals over space-time of seed operators localized to brane-sized regions, and maybe this integral involves some weight factors that depend how far away you are from the Big Bang or something, or other there might be some way to get Boltzmann branes. You may need weight factors to exclude Boltzmann branes, or to enormously dilute and reduce the likelihoods of theories. And I'm saying the analogous problem for a multiverse, which should be considered, it seems much less severe. So, and it's also not clear to me how important long-range quantum correlations and entanglement are for observations, or complexity for that matter. I don't understand yet how complex. Okay, so that's a bunch of ideas that, they're a little bit outside the main topic of the talk, but I hope they can stimulate some talk, and maybe some of you that understand complexity theory better can relate them to complexity. So thanks.